In this video, we're going to look at another way that quadratic equations can be written, and we're going to look at some of the key features of this form. To begin, we're going to do some analysis of the equation that's given to you inside of the red cloud. And the equation is y equals 2 times the quantity x minus 5 times the quantity x plus 3. And this investigation is featured on page 189 of your textbook, and we're going to walk through it together so that we can start to reveal some of these cool features and patterns of this particular type of equation. So the first thing that we're asked to do is to show, create a table of values that will allow us to show that this is in fact a quadratic relation, even though it doesn't look like our vertex friend form of a times x minus h squared plus k. So let's sub in x's value into both of these locations and see what the resulting y value is when we do the math on the right hand side. And I'm going to do this in my head. If you need to pause and use a calculator at any time just to reinforce your thinking, you're welcome to. I'm actually going to begin a little unconventional. I'm going to begin with x equals 0. So if x equals 0, I know that this becomes negative 5 and this becomes positive 3. And negative 5 times positive 3 would be negative 15, and then doubled would be negative 30. Okay? I'm going to continue to work down all the positive values first, and then I'll go back and do the negative ones. So if I sub 1 in now into x, I'm going to have 1 minus 5 is negative 4 for this term, and 1 plus 3 is 4 for this term. So negative 4 times 4 would be 16, or negative 16. Doubled would be negative 32. Let's put the value of 2 in. 2 minus 5 would be negative 5, or sorry, negative 3. Let me try that again. And 2 plus 3 would equal 5. So negative 3 times 5 would be negative 15, and doubled would be negative 30. Let's continue on putting in the values of 3, 4, 5, and 6. I invite you to pause the video and try it, and then come back and check your answers with me. Do that now. All right, check your math versus mine. It's important that you can derive this and not just copy it down from me. Okay? Now, in a similar fashion, pause the video again, and this time we're going to do the negative values. I'll model negative 1 first, and then you can try with negative 2, 3, and 4. If I put negative 1 into this first set of brackets, I'm going to end up with a total of negative 6. And in here, I'm going to end up with negative 1 plus 3, which is positive 2. So negative 6 times positive 2 would be negative 12. Doubled would be negative 24. Okay, pause and try the other three. All right, now, I don't know if you see this, but there's a pretty cool symmetrical pattern following down this y-axis that we've seen before in exploring quadratic functions in other ways. To prove that this is a quadratic function, let's review how to do first differences and second differences to make that point. So I'm going to just show, using these little zigzaggy type brackets, what the difference is between points 2 and 1. Okay, and remember, again, in order to apply differences, we have to make sure the x values are going up by the same increment, and they are. They're all going up by 1s, so that's good. So go to 18 to 0, I go down 18. And to go to negative 14 from 0, I go down 14. And then I go down 10 to get to negative 24, and down 6 to get to negative 30, down 2, and then I start to come back up. Now I'm getting more positive. Okay. If all these first differences were constant, we would know that this is in fact a linear relationship, but of course they're not. Let's try taking the differences of the differences, which of course is the second differences. And we notice that going from negative 18 to negative 14 is a rise of 4. And to go from negative 14 to 10 is also a rise of 4. And as we continue down this first differences column, we notice that all of the incremental skips from one point to the next are all +4. So because these are constant, these second differences, we know that this is in fact a quadratic equation. Now what I'd like to do is take a moment to graph it, and you have the graph on your handout. You'll notice that your x-axis goes up by 1s, and I'm just going to have mine go by 2s because of limited space, and your y-axis goes up by 2s. Mine might go up by a different amount as well. I'm thinking to myself, the most extreme point that I have to plot for this is 1, -32. So I'm going to need to have a y-axis that goes down to at least -30 with a bit to spare. I think I might, just for the sake of modeling here, go by -5s. So -5, -10, -15, skipping by 5s all the way down to -30, so that I can plot that 1, -32 point approximately here. Okay, and then it's done. Similarly, I'm going to go up by 5s this way as well. Okay, and you can do this accurately on yours. I also noticed that there's some other cool points to plot. I noticed that this one here has a y value of 0, and so does this one. That means that they are intercepts, and because they cross or have a y value of 0, they cross the x-intercept. So I know that I've got a couple of x-intercepts at -3 and +5, right here and here. Okay. Now you could go through and plot these other points a lot more accurately on your handout. I'm going to just give us an overall picture of what this graph looks like by doing a rough curve. And I know 618 is way up here, and -418 is way up here. I'm just giving myself a full range to do sort of a smooth curve. Remember, you don't want that to be pointy at the bottom like a letter V. For parabola, you always want it to be like a letter U. And I'll put arrows on both sides, and like I say, you can pause and you can make yours on your graph even better than mine, because you've got true graph paper to work with. All right, now again, some key features of this. We can see down here is the vertex, and it's located at 1, -32. I'm just going to draw that in. I also notice I have some x-intercepts here at, I'll put it here actually so you can see it, at 5, 0, and at -3, 0 as well. All right, let's go into some of the analysis questions that the investigation asks you to complete. First, it says, where are the x-intercepts and is there a relation to the equation? Well, we located them right here and here. And is there any relation to this equation? Well, I do notice that inside the brackets there is a 3 and there is a 5. But I do notice that the signs are opposite. I notice that the x-intercept here of -3 says +3 here, if you will, and that +5 says -5. Well, that would be really cool if this section of the equation, when it's written in this way, tells us what the x-intercepts are, and it does. I'm going to show you why that works. If we take each one of these pieces, each of these x-intercepts separately, we know that x minus 5, when we have a y-intercept, has to give an x-intercept has to give a y value of 0. So what if we set that equal to 0? And what if we solve for x? Well, in solving for x, the -5 has to come to the other side of the equation, or you think of it as adding 5 to both sides, and we get x equals 5. So the same thing can be said when we take just this piece and set it so equal to 0, because if it equals 0, then the entire right side equals 0. Same here, if this piece equals 0, then the entire right side equals 0, and therefore the left side, or y, is 0 too. So let's do x plus 3 equals 0. And when we move the -3 over, or I'd rather think of it in terms of subtracting 3 from both sides, we get x equals negative 3. And that corresponds perfectly to our diagram. Okay, so it would appear that this equation gives us intercept information kind of by inspection. Next, it asks us, can we find the vertex somehow using the x-intercepts? Okay, this thing right here. Well, what's great about parabolas is we know that they have a line of symmetry that goes right down the center. And what's neat, if I draw out this x-axis in a little bit more of detail here, if I go from 5 all the way down to negative 3, where the other x-intercept is, here and here, I notice that the coordinate of my vertex is 1. It's right here. And I also notice that, I'm not doing this to scale, but it lies on the axis of symmetry, right? X equals 1 is the axis of symmetry for this particular parabola. So is there a way that I could use the x-intercepts to find the coordinate of the vertex? And the answer is yes. It's in the center between these two. So, if you have nice integer values to work with, you could leapfrog in from the right at an equal pace. Here I went in 2 on both sides, and if I go in 2 more, I land in the middle. Okay? If these x-intercepts are not integer values where leapfrogging or skipping in is easy to find the middle, you could just find the average of them too. You could say that 5, add them together, 5 plus negative 3, and divide by 2 would be the middle or the average between them. 5 plus negative 3 is the same as 5 minus 3, which is 2, and 2 divided by 2 is 1. So we can find the average as well. Nice. So, big idea. How can we find the x-intercepts and the vertex when we see a quadratic in this form? Okay. Well, it's time to point out some key features of this form. It's called intercept form, or sometimes you'll see it as factored form because it looks an awful lot like some of the binomial multiplications or and factoring that we did in the previous unit. Okay. So what we need to know is that the value of r, not what you see, but what it actually is, because there's a negative in front of it, r and s are the intercepts of that parabola. Okay, and again, not the sign you see in front, but the sign it truly is when you sub in. So another way of thinking of it is it's the opposite of what you see. This a that's out in front, right here, is the same a that we had for vertex form. This a, if it's positive or negative, tells you if it's upward or downward facing. Notice for ours, it's +2, and we have a happy face or an upward facing parabola. And because it's not a value of 1, it has a stretch factor, and you find when you graph this, even despite the increments you count it, this is a more narrow parabola or stretched parabola compared to y equals x squared. So we can see that it's upward, and we can see if it has a stretch or compression factor. So there's a lot of good information that comes directly from inspection from a quadratic written in this form. The only thing it doesn't tell you directly is the coordinates of the vertex. Okay? Now the other thing that we're missing in the vertex is that we found the y coordinate of it quite easily, but how could you find, or sorry, we found the x coordinate of it easily. How could you find the y coordinate? Well, what happens if you plug x equals 1 into the equation? We did that over here, and we noticed that plugging in a value of 1 would give a y value of negative 32. So if we know the y coordinate, we can find if we know the x coordinate, we can find the y coordinate by subbing into the equation. Sorry, that's not very clear. Let me try that again. Sub into equation. All right, let's look at a couple more examples. In our next example, we are asked to describe and sketch the graph of a quadratic equation and to tell a little bit about it. So let's write that equation here. It's y equals 2 times x plus 2 times x minus 4. All right, so this is all we're given. It's a quadratic to intercept, or sometimes we call it factored form. And we are asked to talk about, first of all, its general shape. So where do we get that information from? Well, the general shape has to do with, is it up or down? And is it stretched or compressed compared to y equals x squared? So we get that information, as I just said earlier, right here from the a value. So because it is positive, we know that this is an upward facing parabola. And because it has a value greater than 1, we know that it is stretched compared to y equals x squared. It has a stretch factor of 2. Next, we're asked to find out what are the x-intercepts of this particular parabola. So for that, we go to these little sections right here, the binomials. And we know that when we're talking about an x-intercept, y has to have a value of 0. And the only way we can get y to be equal to 0, the 2 can never be 0, but one of these could be equal to 0 and the entire side would be equal to 0. How do we make this equal to 0? What value of x makes it 0? Well, let's find out by writing this and rearranging. So if x is negative 2, this binomial would become 0. But there's another value that would make it work as well. If x were equal to 4, then this would become 0. And then the whole entire equation would read y equals 0 as well. So we can say there are two x-intercepts. The x-intercepts are negative 2, 0 and 4, 0. The next thing we're asked to find is the axis of symmetry. So, as we saw earlier, the axis of symmetry is in the middle between the two x-intercepts. So we can do it one of two ways. Because these are integer values, we could draw a number line and ask ourselves if we were to skip from 4 towards negative 2 or negative 2 towards 4, where would they meet in the middle? Well, if I skip 2, I would get down to 2. And if I skip 2, I would get down to 0. If I skip one more, I find that 1 is in the middle. So the axis of symmetry is x equals 1. If I didn't have nice numbers to work with, I could just find the average of those two numbers by adding them together and dividing by 2. So on the top I have negative 2 plus 4, which gives me a value of 2, divided by 2 gives me 1. And there you go. The axis of symmetry would be x equals 1. How can we then find the vertex? Well, we can find the vertex by taking this axis of symmetry value and plugging it into the equation. So the value of y for the vertex is equal to 2, and let's sub in 1 where there was an x, so 1 plus 2, and sub in 1 where there was an x, 1 minus 4. So I have 2 times 3 times negative 3. 2 times 3 is 6, times negative 3 is negative 18. So the vertex has a coordinate of 1, negative 18. And there you go. All kinds of information about this parabola just from inspection or a little bit of mathematical work when it's written in intercept or factored form. Last example. Many of you are familiar with the McDonald's symbol, the big capital M. Let's imagine that that big capital M for the McDonald's sign, I don't have a yellow marker, but I'll use orange instead. Let's assume that it is two parabolas that are upside down. For this question, I'm going to take just half of that parabola and do some examining with it. Okay. The dimensions of this arch are 22 feet across, if you're taking down a real sign, and 20 feet high. It's big. We're asked to sketch this arch on the axes by putting its left base, which would be this thing here, right at the, 4 units to the left of the y-axis. So if we did that, 4 units to the left, we'd be putting it here at -4. Okay, so let's let it start there, and let's draw it in. And I'm not drawing it to scale, this is just a sketch. And as long as key features are labeled, it doesn't have to be to scale. All right, label the x-intercepts in the vertex. So -4 is where it starts, but we know it's 22 feet across. So if we go 22 feet across, where will we end up? Well, what is -4 plus 22? I have more positives by 18. So this would end up being at 18. Like I said, this is definitely not to scale. We've labeled the x-intercepts. Where would the vertex be? Well, let's remember again that the vertex lies on the axis of symmetry that goes right down the center of this parabola. So, where's the middle? Let's start with the x-axis first. Now you could do leapfrogging from -4 inward and 18 inward to find the middle. I would challenge that that probably is going to take a little bit longer than just adding them together and finding the average. So let's do -4 plus 18 and divide by 2. I have an excess of 14 positives on the top, which means that 7 is right here. And again, remember, we're not doing this to scale. So if I want to find the coordinates of the vertex, I know that it's 7 something. How do I find the something? Well, I can plug it into an equation, except that I can't in this case because I don't have an equation. How could I get an equation for this parabola? And let's remember that the equation that we're looking at today is in factored form or intercept form. So when we find an equation of a parabola, we need to find values for a and r and s. And then we can leave the x's and the y's alone because that'll represent all points that are on this specific parabola. Can we fill in r and can we fill in s? You bet we can. We've got our -4 here and our 18 here. So let's plug those in. X minus -4 times x minus positive 18. I'm going to take a second here to simplify the signs so that we don't have any miscalculations. So we have x plus 14, plus 4, and x minus 18. We almost have an equation that we could sub this 7 in to find the y value, except we don't have an a value. So in order to find a, we need to sub in some other point that lies on this parabola. Okay, could we find another point? And the answer is yes, we can. Okay, I'm going to backtrack for a second because I realize we have another piece of information here that we can include. I just realized that we have this 20-foot high piece, don't we? So if it's 20 feet high, that means from the ground to the top is 20. We do actually know the coordinates of the vertex because we were given that. Okay. Now, let's go back to finding the equation of this arch. We need one more point to sub in to the x and y values so that the only thing left is a and we can solve for it. We do have one more point we could sub in for x and y that lies on this curve. We could sub in the vertex. So let's do that. The y value of the vertex is 20. We don't know A. The x value of the vertex is 7. And I'm going to put it in for both x values, here and here. All right, let's solve for what's inside these brackets. So I have 20 is equal to A times 11 times negative 11. Now this looks kind of funny right now because we're used to seeing terms with the numerical coefficient first and the literal coefficient written second. And this has it backwards. It has the numerical piece at the end and the literal piece first. Nonetheless, they're still all being multiplied by each other. So we can change the order of this, and I'm going to include this here as an example so you can see how it works. We can do negative 11 times 11 times A, and then it becomes in a form that we're pretty familiar with. So 20 is equal to, well, negative 11 times negative 11 be 121A. If I want to solve for A, it's not by itself, it's being multiplied by negative 121, so I'm going to do the opposite, or the canceling process, to multiplying by 121, which is to divide by negative 121. And so A is equal to negative 20 over 121. And that's okay if it's a fraction. No big deal. Okay? And we're just going to leave it as a fraction like that. We don't have to change it into a crazy decimal. Just leave it alone. Okay, so therefore the equation of this parabola for McDonald's is y equals, let's put our A value in, negative 20 over 121. And then let's put in our x-intercept values. Okay, we have x plus 4 and x minus 18. Don't forget that what you see in the equation is opposite to what you graph because of the negatives in the general formula. All right, enjoy your practice. Let me know if you have any questions, and welcome to Intercept in factored form.